Okay. And this, there were some glitches in what people did, but everybody had a pretty good idea where to start. What I'm gonna tell you, here's how we're gonna start. It's a common way. I'm gonna do it unless I do it a different way. Okay, and it'll be the common way you do it unless you choose to do it a different. There are equivalent ways to do this, but the way that kind of brings everything together mathematically is just to write every vector in terms of its I and j components. Write it as a sum of an I and a j component. And of course, the I component is the x component and the j component is the y component. Okay, so I'm going to say that, okay, let's see. F1 equals F1 cosine theta. All right. F1 sine theta times the beta vector. This assumes that theta is measured counterclockwise from the positive x-axis. So that, for example, when we do F2, we're not going to use 15 degrees for the angle. We're going to use 255 degrees, because that's what it is if you start the positive x-axis and go counterclockwise. That automatically takes care of the signs, plus and minus signs, not trigonometric signs. Okay. So, well, that's pretty easy. You do 5 times 5 newtons times the cosine of 30 degrees I plus 5 newtons times the sine of 30 degrees times J. Okay, that's approximately, let's say 0.87 times 5 is 4.35. We say about 4.3 might be 4.2. 4.3 newtons times I plus 2.5 newtons times J. Okay. Now, what does that mean? That means that F1x is 4.3 newtons times I, and F1y is 2.5 newtons times J. And again, as I said last time, and we'll see in lab, if you close your eyes, you can't tell if somebody's pulling on you with a 5 Newton force at 30 degrees, or you got 2 people teamed up, one of them pulling in the x direction with 4.3 newtons, the other pulling in the y direction of 2.5 newtons. Has identical effect. Okay. Okay. So that's what we mean when we say that F1 is equal to this. A 5 Newton force at 30 degrees is totally equivalent to a 4.9 Newton force in the x direction and a 2.5 Newton force in the y direction. And you want to really understand that statement. Okay? Because it makes sense of everything we're doing. Now, F2. Okay. Now, a radian's about 60 degrees, it's 57.1 something. Okay. So approximate 60 degrees, this is pretty close to a quarter of a radian. A little less than a quarter. Okay. So I'm going to say that the sine of 255 degrees is a little less than a quarter. And if you don't understand radians and approximations well enough to do that, well, that's not unusual. But I'll kind of explain some of that in more detail. I'm going to say it's about 0.24. If that's 0.24 by the Pythagorean theorem, 0.24 squared is about 0.7. Actually, it's about 0.6. Yeah, 0.525, 0.0525, 0.06. So that would be 0.94, so that the cosine was 0.97. So this is approximate, and this is approximate too, because even if you punch it into your calculator, if you don't have the rare angle that has integer components, you're going to get an irrational number that never ends, so you're approximating it, no matter how many figures you use. Okay, so it's approximately, and 8.7 newtons times I plus 2.2 newtons times just, okay, be 2.1. Runs off to 2.2. You know, with my approximations, and your numbers ought to be pretty close to those. If they aren't, if you use the calculator, it probably means I screwed up, but you get the idea. These aren't too far off. Now, I said this, and it's a lie. Because we're not dealing with 55-degree angle or 15-degree angle. We're dealing with a 75-degree angle. So I've got the sine and cosine reversed, and I don't have the right plus and minus signs on them. So I just did something. And what did I do? I pretended I made a mistake so I could make a point. I do that a lot. Okay. First of all, do you have a picture of what it is to add these two vectors? Did you write down this picture? I think everybody wrote down this picture. If you wrote down this picture, it wouldn't take much effort to put, let's say, this vector head to tail, this vector, and estimate, or use a parallelogram and estimate a solution. So, what's that sum look like? Well, it's not quite 5 in this direction, because of course, this isn't quite 5, that's 3 instruction. I'm going to say maybe that's I estimate the sum. I'm going to say that's maybe something like about 3i minus 7j. Okay. Just deal with these numbers and stuff. That looks plausible. Clearly, the I is going to be a lot less magnitude than the J, and the J has got to be negative. Well, that wasn't going to happen with the numbers I have there. Okay, so what I've got to look at is cosine of 225 degrees is about your negative 0.24. So this will be about negative 2.2i. And this number should be your 0.97. And this should also be negative. Well, plus this is negative. So you put in the correct sine and cosine. You're in the third quadrant. They're both negative. So as soon as I put down positive numbers there, I should have said, wait a minute. Okay. Okay, so then we're going to have negative 0.87, 8.7, sorry. I didn't write my newtons, but I'll kind of back them up. Okay. Okay, well, then. F1 plus F2 is this plus this. Well, your I's are independent of your J's. Okay, if it's in this direction, then none of it is in this direction. And independently, if it's in this direction, none of it's in this direction. Those directions are totally independent. They're linearly independent, just to use a term that brings out harm in people who've had the linear algebra class. Not y'all did well in the linear algebra class. So linear independence. Just the idea, though, that the components are totally independent. That's going to be really important in a couple of weeks. Okay, so F1 plus F2. Well, you got your 4.3 newtons times I minus your 2.2 newtons times I plus 2.5 newtons times I minus 8.7 newtons times J. However you want to line that up, however you do, whatever number of steps you want. Once you have F1 and F2, you easily write out F1 plus F2. Now, having done that, we see that this is 2.1 newtons times I minus 7.2 newtons times J. Is that close to what you got? Okay, so you see again, I was a little careless. You know, 2 minus 8 is negative 6, right? I wanted 7 because that was my estimate. I wanted my estimate. Well, I'm reasonably close to my estimate. This is a hand-drawn picture. These things aren't really to scale. And yeah, this one should angle a little more this way. I probably still would have estimated 3. 2.1 I minus 6.2 J. Okay, so now my question is, well, let's just go. The next question that immediately arises is what's the angle and magnitude of this vector? How big is it? And what's its angle? What's its direction? Okay, so we'll find that in a minute, but let's go ahead and calculate the dot product. Then we'll come back to get the angle and magnitude. So the dot product, as you know, can be calculated in 2 ways. Magnitude of F1, magnitude of F2 times the cosine of theta. That's one way. Now we've got the components, so we can also calculate it with the components and see if they come out the same within there. Okay, so well, the magnitude of F1 is 5 newtons. And I'm going to suppress newtons now. You know, this would come out in Newton squared, and this would come out in Newton squared. But we're mainly after the angle and stuff like that. So let's suppress the units for the moment. So it's 5 times 9 times the cosine of one angle. Well, the angle between these vectors. And it would be the smaller of the 2 angles between the 2 vectors, which will always give you a positive or negative number, depending whether that angle is greater than 90 degrees or less. Well, the angle between the 2 vectors is here. It doesn't matter if I go from here to here or here to here, so I'm going to put 2 heads on that little angle. And say, well, the magnitude of that angle is the cosine is an even function. Cosine of a negative angle is the same as cosine of that angle. So it's not going to matter. So whether if I go from here to here, I get a negative angle. If I go from here to here, I get a positive angle. Might as well just use the positive angle. Again, since the cosine is an even function. Okay, and what is this angle? Well, you got 30 degrees here, you got 15 degrees here, and you got 90 degrees here. 135 degrees. So that equals 40 times negative square root of 2 over 2. And you should know 135 degrees is at a 45-degree angle with both axes and so forth. And as I mentioned before, know how to get square root of 2 over 2. And, you know, back in the good old days, we memorized the square root of 2 as 1.414, knowing that there were more significant figures. We could look up in a table if we needed them, because we didn't have calculators or computers. And square root of 3 over 2 is 1.7. Well, square root of 3 is 1.732. Okay. So square root of 2 over 2 is half of 1.414, which is 0.707. So that's approximately equal to 0.71 times 40, which is 28.4. I'm going to say 28.3. And it's negative. Okay. Now that has a lot of significance. Significance. There are times when we want to project vectors on others and stuff like that. But I don't think anything in this introductory stuff is going to ask you to do projections at this point. And when we do it, actually should be pretty well sure. Okay, so that's one way to do it. Now let's see if that agrees with what we get. We do F1 dot F2. Looks like I'm just about to disprove one of mathematics. Incidentally, should have been 45. I got 40, and that changes things. 5 times 3 times 5. That should be about 31.8. Is that angle really 135 degrees now? And Lily Albertson, so that's what we're doing here. Right back there against this. How much signs of that? I wrote down F1 plus F2, where I should have written down F2. I don't get any look. Yeah, you see, again, I'm pulling out some machinery to check myself. I want to get something that doesn't make any sense. You kind of want to get in the habit of doing that, because you will get stuff that doesn't make sense. Okay, make one small error. Some of the angles are other. But project this on this, it makes sense. Okay, well, linear algebra okay, you get negative 2.2 I minus 8.7 J. Okay, I'm going to do the arithmetic honestly. 2 times 4.3 is 8.6, and then I add 0.86 to get 9.46. I did that quick. I don't know what's wrong with that. It's, okay, and 2.5 times 8.7. Well, 2.5 times 9 would be 13.5, and 0.3 times 2.5 is 0.75. So I think that would be it's 1.5 times 8.7. Yeah, and 8.75. Okay. Now that I boxed up all the arithmetic, see what these add up to. That's going to be negative 30.91. So I did something wrong, but it's pretty close. So if you do it with your calculator, it's probably going to come out right. I did quite a bit there with a rapidly decreasing capacity for working memory. So there it is. And I'm kind of demonstrating, in fact, though, that you want to know about what you ought to get. So I can do a quick ballpark approximation, just two significant figures. You know, that's a little more than -8, and that's like -20. So I'm thinking maybe in the ballpark of -28, just with a much easier, quicker calculation. Just 4 times 2, it's going to be a little more than that. And 2.5 times 8, which is 20, which you calculate easily. It's going to be a little more than that. It's going to be negative. So makes sense. There's a consistency here. There are also pictures you can draw. I started to draw one. You know those pictures. You remember the linear algebra projections and stuff like that. They can help you, but it's not necessary. Okay. Still, the more insight you have, the better. Now, the basic ballpark procedure is just everything starts just by doing this. This is easy to do. It's easy to remember. Okay. You do it a couple of times and you get used to it. Then you just add these. So this and this means I's are unlike J's because they're totally independent. So you add the I's and you add the J. You get the sum. You can, if you have this information, you know what the angle is, so you can calculate the dot product very easily. And of course, if you calculated the components, it's equally easy to do the dot product. Okay. And what you get ought to be consistent. I would say these are consistent. They're not exactly equal. They're consistent in that they're within my capacity for approximation. Should be clear from that. Now, I want to come back and talk about what's the magnitude of F1 plus X. So let's repeat. I keep reminding myself of this is Newton's. Engineers love to leave units off of things and stuff, but they got their own tricks for keeping track of units. Okay, so we'll let them go. Okay, we'll be tolerant. Okay. What's the magnitude of that? Well, we got a picture. Not a good picture. Here's F1 plus F2. And here is F1x, which is 2.2 newtons times I. It's 2.1 newtons. And F2 is, F1 was negative 6.2 newtons. Times your J vector. Oh, right here we have the right triangle. I draw this right triangle. A little more accurate. Maybe I'll have a 2.1 here and a 6.2 here. It's negative 6.2 here, but you just take the triangle out and measure its sides. They are 6.2 and 2.1. We'll just rub it in on the engineers, all right. Okay. So magnitudes are represented by this side. How do you calculate that? You use Pythagorean theorem. This side is the square root of 6.2 newtons squared plus 2.1 newtons squared. And that's approximately equal to the square root of about 39 plus 4.4. And now the newtons are outside the square root sign because you have newton squared here, newton squared here, factor out a newton squared from the square root and up to 3. And that's approximately 23. And I'm going to say that's about 6.6 or 6.7. And probably choosing wrong. It's about 6.6. Okay. So the magnitude of F1 plus F2 is, okay, the square root of this. Okay. And I write it in symbols here because this is generally the case. It is, it's change out to the R usually. Some of these are for the result. Now that this is the R vector, so I can use R here. And the R is whatever you get when you add the vectors up. Now, is it any more difficult to add 10 vectors if you have this magnitude and angle of each? What would you do to add 10 vectors? Well, you'd express them all as I and J components and you'd add them up. So ultimately that means you add up the I components, you add up the J components. It's a little more work. But of course, if you write a program to do it, you set the program up to take any number of inputs. Once you get the inputs into it, you're good. Incidentally, do remember to bring your computers to the lab next time. I said that before. We do want to install the software. I can't install it on my computer because it's controlled by the college. Which means I got to track Adam down. I'm going to do that tomorrow afternoon. Yeah, I don't have administrator access. There's a good reason I don't want to have it, because I shouldn't have it. All the people here, I'm the one who probably shouldn't have it most. Okay, well, yeah, I messed up. I know a little bit stuff, but not much. I know enough just not to get the problem. Yes, hang on. I wrote something down carelessly that might have caused some confusion. Correct. I don't know what it was. The I component of F1 is this, and the I component of F2 is this. We have to add I components to I components. We can't add I components to J components because, again, I and J are completely independent. In this direction, it's definitely not got any component in this direction. Okay. Okay, so when I did that, I just looked up here and said, here are my I components of F1 and F2. So those are the I components. And down here, I have this written as an I, it's a J. We need to be careful about that. But my J components would be this green over here. But the J components are here and here. So right there, we have the J component here and here. Sure, so yes. And this, because here are my numbers. Now I circled this in green and it's almost up. I'm not going to erase green because it won't have much. So, okay. These two numbers here go together to give us this. Okay. And then I should have circled this a different color. Pretty easy to change green to yellow. So keeping track of where the I's and J's are, it becomes pretty obvious what you subtract. And suggestions make, well, if that was 2.5, this is 2.2, this would come out a lot closer to this. It would, but this is the one that's probably more accurate. Another comment. This is more accurate than this could ever be. Because when you do this, it's based on decimal approximations of the components of F1 and F2. Okay. This is based on the magnitudes and the angle, and we know the exact magnitudes and angles. Now, if it's actually experimental data, we don't really know exactly what they are, because everything's got uncertainty, and you're dealing with that in some of the homework problem. So that's just a side comment. Okay, one more thing I want to do though is I want to take this picture and get down to the essence of the components. So colors myself here. But here I've got my F2x. Now I should have written the newtons to be consistent with what I've got here, but I don't have a lot of room. And my F2y equals negative 8.7 J. And I'll put an N there. Just be consistent. And that should be clear. You just project this up here, project this over here. Then you've got a representation of those. We calculated approximately what they would be. Okay, well, that means that my whole picture could be reduce just to the components. So that I'm going to have Fx 4.3 newtons times I. F1x. F1y is 0.5 newtons times J. F2x, I'm going to make sure you put the column. Well, F2x and F2y look like this. So F2x is negative, that's F2y, obviously. Negative 8.7 newtons times J. And F2x equals negative 2.2 newtons times your J factor. Okay. As I've said, these two forces are completely equivalent to this one. And these two forces are completely equivalent to this one here. You can't quite see, but push the limits of the camera. Okay. It always zoom back, but it keeps thinking this one. Okay. So that this is totally equivalent to my original picture. With F1 and F2. Again, because these two vectors are completely equivalent to this. They combine to give you the same exact effect. And these two vectors are completely equivalent to this. I said the same exact effect up to round off error and whatever else is going on. Okay. But this vector can be replaced by these. This vector can be replaced by these. So that when you add them, what are you doing? Well, your X components are 4.3 newtons this way and negative 2.2 newtons on the X direction. You just add this to this and it's like you take this vector and put it head and tail with this one. And the vector from here to here is going to be the X component of your result. And if you take this vector, 2.5 newton times I, and add it to the vector down here, just put those two vectors head and tail, you see that the resultant vector is from here to here and from here to here. It's the result of these two components. And this is not drawn to scale, so it's not going to look quite right, but you get the idea. And you want to understand that. You want to understand this whole picture, every detail of it. Now, your book will also tell you, well, you can make a table. You can put your X components in this and your Y components over here. Okay. So we could have made a table. We could make one if we had a little more room. I guess I can pull it. Okay. Sometimes it's convenient to do a table. You could also 1/5, where F1 has X component 4.3 newtons, and F2 has X component negative 2.2 newtons. And the Y component here is 2.5 newtons. And here is negative 8.7 newtons. So F1 plus F2 has a component of 2.1 newtons. And this one has a component of negative 6.2. That's several ways to see the same thing, just the sum of two vectors. You should understand totally every detail of that, so that you have the deepest understanding, or deeper understanding you have. Okay? And the deeper your understanding, the less trouble vector operations are going to give you. Okay, well, now everybody's doing well with units and conversions and all that stuff. Okay, I don't see where anybody's having trouble with that. Some of you didn't quite have time to finish everything. Okay, so I might go in there and give you a little extra time to finish it. Get all the points. And they, you know, I think they rated this assignment, what it was due today, as something like 2 to 2.5 hours or something like that. Okay, it can easily take twice that sometimes, especially if you're not real familiar with the mathematics. And if you are real familiar with the mathematics and you've done it, like if you're taking statics, you might go through this stuff pretty quickly. Okay. Of course, you're taking statics and you're still working out other stuff. It's quite taking a little long. That will be done with the preliminaries as of this next assignment. Then we're just going to dive into uniformly accelerated motion. If you understand this much about vectors, you'll be okay for quite a while. But we're going to go ahead and finish up the whole thing. Okay. So the one really kind of new thing that you see in this assignment is the cross product. You had linear algebra, I think we did some stuff with the cross product, a whole lot of it. Or maybe we didn't, I don't remember. Okay, I do all this stuff in a variety of courses. Sometimes forget what I did in one course or the other. Sometimes in the same day in the same class. Okay. Okay, well, very simple. Now I'm going to introduce it this way. Text and so forth will introduce it in another way. And you do want to be reading the text along with, you know, if you're in chapter 1 working the problems, you at least want to scan through chapter 1 so you know what's in there. So you got to get some explanation, some correction from open math. Hopefully you're getting some foundation in class. You put all that together and get cool. So I'm going to introduce cross product this way. First, I'm going to introduce it in my hands. Now, and you want to watch my hands. I's in this direction, J's in this direction, and K is in this direction. Each one is independent of the others in that each one has no component in the direction of the other one. No part of this one is in the direction of this one because they're at right angles, and this is at right angles to both of them. Okay, so put my fingers in the direction of I, and my palm is facing so that when I turn my fingers, they point to J. Then this points in the direction of I cross J. Cross product is a vector that's perpendicular to both vectors. Now there are two vectors that are perpendicular to I and J. One of them's up, one of them's down. The one that's I cross J is the one that's up because of the right hand rule. If you do this with the left hand, you're gonna have to turn it this way and you're gonna get it down. So make sure you know which one is what. I keep this thing in my left hand, so I know. I forget over there. If I accidentally put this one on and put this one away, then I'm in big trouble. I could get all my cross products wrong. Okay, well, also, if two vectors are perpendicular, the magnitude of the cross product is the product of the magnitude. In other words, in this case, I have magnitude 1, J has magnitude 1, they're both significant. And they're perpendicular. So when I do their cross product, I have to get a unit vector. That's why it's not just any vector in the Z direction, it's the K vector. Okay. Now I'm just going to write down the other two. Actually, I'll demonstrate. What's I cross K? Well, here's the direction of I. If I put my hand like this, my fingers won't go toward K, will they? So I got to put my hand like this so that my fingers will go to K. And there's my direction. That's the negative Y direction. That's negative J. And then what's J cross K? Now I got my now I got to put my fingers in the direction of J so that they turn toward K, and that gives me I. Now you can, if you get confused with the right hand rule, probably find all kinds of YouTube videos of people demonstrating it. Okay, in different ways. So if this isn't clear to you, you know. The other thing is, what if I did J cross I? Well, J cross I gives me negative K. So that if I reverse these things, this isn't commutative, it's an anti-commutative. Okay. You can see with your right hand, J cross I is negative K. And you can check it out yourself. K cross I equals K. And K cross J is negative I. So that vector B crossed with the vector U is equal to the negative of U cross V, whatever U and V are. Now I'm going to show you the long way to calculate a cross product. Your text, other sources, show you a short way, determinant way. And if you don't remember determinants, look it up. Okay, I might do one depending on how much time I have. So now I'm going to let A just equal a combination of an I and a K vector, some multiple of I. So, you know, if it's 5I and I is this long out this way, then it's going to be this long 5 times. And whatever J is, -3 or whatever K is. If K is this long, -3K will be this long, it'll be down, right? And let B this. But there's one more thing I guess I need to tell you. The other thing is that I cross I equals J cross J equals K cross K equals 0. What I said before is if the two vectors are perpendicular, then their product is the product of their magnitudes. Okay. If they're parallel, the cross product is 0. And there's another rule about the cross product. I'll write down. I'll tell you how to calculate it. Hard one. And maybe I'll tell you how to calculate it. Actually, what I'm going to do is probably the easy way to do these vectors that each only have 2 components. If they both have 3 non-zero components, you probably want to put them into determinant. So here we just use a derivative law. Okay, well, I'm just going to state that cross product distributes over addition. So this gives us A1I times B2J plus B3K plus A3K. And I said times its cross product. Let's get to that. Rewrite it. Class before this is elementary algebra. And we're just, emphasizing distributive law today. So not that I wouldn't have done that otherwise. A1I cross B2J plus B3K plus A3K cross B2J plus B3K, which is then A1 B2 I cross J. You've got A1 times B2J, right? And then just crossed with B3K. Then we've got A3 B2K cross J. A3 G3 K cross K. What's I cross J? We look at the table, or you can just do it. I cross J is K. Once you get you want to do it, you don't want to be looking at a table, but do it with your hand, do it with your imagination, then look at the table, but be sure you were right. And I'm pretty sure you always get it right. So you got to have A1 B2K, and then you got A1 B3 times I cross K. Well, I cross K is negative J. And then A3 B2 times K cross J. K's here, J's here, negative I. When I wrote 0, I should have written 0 in the vector because it is a vector. So And then this is the zero vector. This K cross K is the zero vector. Anything times zero vector is the zero vector. And it's scalar. Okay, so now if I put this in the order of A, D of I, J, and K, it's negative A3 D2I minus A1 D3 J plus A1 D2 K. Now, another definition of the cross product. This is how you can calculate it. One way you calculate it with determinants. I don't have time just to write that down. But the other thing about cross product is that's good perpendicular in there. Perpendicular. Both A and B. By the right-hand rule. So if A, you want to watch what point, if A is that way and B is that way, then fingers here, cross toward this, all has to be facing it, so your fingers really cross that way. Your cross product would have to be in this direction. If you did B cross A, the cross product would be in the opposite direction. And magnitude of A cross B is magnitude of A. That's magnitude of B times the sine of the angle between them. Much like the magnitude, well, much like the dot product, okay? But it's the sine. There are two things. The dot product is zero if two vectors take a right angle, isn't it? If two vectors are at a right angle, then theta is 90 degrees. And the sine of cosine of 90 degrees is zero. And that's really important. Okay. The cross product is zero if the vectors are parallel. So it's one test, for example, to see whether two vectors are parallel. We usually don't use it for that purpose, but we can. And sometimes it does come in handy. The other thing is, okay, back to our example. Actually, it's not even the previous example. Don't have time to write out all the conditions here, but obviously, I mean, A is A1I plus A2J plus A3K. B is B1I plus B2J plus B3K. We just calculate this determinant. And this determinant can be expanded in minors. Here. Okay. Navy SEAL. I'm getting kind of leave myself enough room. Anyway, then you got K times A1 B2 minus A2 G1. So you got three ways of calculating a cross product. You can do this, which is really pretty easy if you only have two components for each vector. Okay, so this is worth kind of knowing. It's just distributive line. You just know what I cross J and J cross K and everything is. This is real easy. If you have three separate components, you probably want to write it out like this and just use the rule for determinants. Now, if you haven't done determinants in a while, and some of you have done the arousal solution, if you haven't done determinants in a while, you want to review it, but it's simple. It's a simple calculation procedure. And then down here, if you want to memorize this formula, you can. That would be my last choice. That formula, just keeping the pluses and minuses straight. It's much easier if you write this. This is much easier to remember. And this is just an application of the distributive law. You could always do that. But again, if you have three components, then you got 9 things to evaluate. It gets messy and error. So this is the way people would usually calculate it, unless you've got a pretty simple vectors in this case. You probably do it this way. I don't think anybody in their right mind would do it this way, but don't take offense if that's the way you decide to do it. Okay.